Welcome to the Sleepy Scholar. It's lovely to have you here tonight, wherever here happens to be for you. Maybe you're lying in the dark, with the blankets pulled up to your chin. Maybe there's a single lamp still glowing somewhere across the room, and you keep meaning to turn it off. And you haven't yet, and that's all right. Maybe you're on a train, or a couch, or the floor, or a bed that isn't your own. Wherever you are, and whatever time the clock is showing in your corner of the world, I'm glad you found your way here. And I'm curious, honestly, where in the world are you listening from tonight? If you feel like it, and if you're still awake enough to type, leave a little note somewhere down below and tell me. It's a quiet thing, but I like knowing there are people out there in all their different dark rooms, all settling in at once. Before we drift too far in, let me say one small thing, and then I'll let it go. If you enjoy these slow journeys, and you'd like more of them to keep arriving on the quiet nights when you need them, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you who've already subscribed, who've been here before on other nights for other subjects, thank you. Truly, it means something. That's all. That's the whole ask, and now it's behind us. Here's my only promise for the next while. We are going to go slowly. We are going to take one strange, beautiful idea at a time and turn it over gently and set it down before we pick up the next one. There is nothing here you need to understand, nothing you need to hold on to. If you drift off somewhere in the middle, if your eyes close and the words start to blur into that soft place between listening and dreaming, that is not a failure. That is exactly the point. The ideas will still be here when you wake. The galaxy has been keeping this particular secret for billions of years. It can wait for you to hear the rest another night. I'll try not to make any of it so interesting that it keeps you awake. But if it does, well, at least you'll have learnt something on the way. A fair trade. So, let's begin, shall we? I want to start with a single object. Not a large idea, not a sweeping tour of the whole cosmos, just one thing hanging out there in the dark, and I want you to picture it as best you can with your eyes already halfway closed. Somewhere out past the bright, crowded disk of our galaxy, past all the familiar stars you might name, there is a smaller galaxy, or rather there was. It's called the Sagittarius Dwarf Spheroidal Galaxy, which is a mouthful, so let's just call it Sagittarius, and picture it as a modest little gathering of stars, a small companion that has been orbiting our much larger Milky Way for a very long time. It's a dwarf galaxy, which is just astronomers' plain word for a small one. Not small the way a pebble is small. Small the way a village is small next to a sprawling city, still millions of stars, still a whole world of its own. Once, and here is the thing about Sagittarius, the thing that makes it the perfect place for us to start tonight. It is being torn apart. Right now. As you lie there, slowly, silently, without a sound anyone could ever hear. This little galaxy is being pulled to pieces as it plunges through the body of our own. 3 astronomers found it in 1994. Their names were Rodrigo Ibata, Gerard Gilmore, and Michael Irwin, and I like to imagine them poring over their data, realizing what they were looking at, realizing that a whole galaxy was in the middle of being unraveled almost directly on the far side of the Milky Way's heart, hidden behind all that crowded starlight, and nobody had noticed until then. It had been dying in plain sight. But here's where it gets strange, and here's the image I really want to leave with you before you sleep. Sagittarius is not just cracking apart into a little cloud of stray stars. As it's pulled to pieces, its stars are being drawn out into a long, thin ribbon. A stream. And that stream, that ribbon of stolen stars, does not just drift off to one side. It wraps, it arcs up and over and around, following its own great looping path until it stretches all the way around the entire Milky Way. More than 360 degrees, a complete loop, and then some. A full circle wrapped around our galaxy, made of the shredded remains of another one. Let me say that again, slowly, because it's a lot to hold. Our galaxy is roughly 100,000 light-years across. That is a distance so large that language basically gives up trying to describe it. And a single dwarf galaxy, torn apart, has been stretched out into one ribbon long enough to circle that whole thing. A whole galaxy, unspooled, smeared across the entire sky. If your eyes could see it painted up there tonight, you would see a faint band of stars looping right over you, and every one of those stars used to belong to somewhere else, to something that no longer exists in one piece. That is where we're going tonight. Not to Sagittarius alone, but to the realization that Sagittarius is not special. It is not the exception. It is the clearest, most dramatic example of something the Milky Way has done again and again and again, all through its long life. Our galaxy is wrapped, threaded, laced through with the shredded trails of smaller galaxies and star clusters it has pulled apart and absorbed. The dark space out there in the halo of our galaxy, that vast, dim sphere of old stars surrounding the bright disk, is not empty. It is full of ribbons, full of trails, full of the quiet evidence of everything the Milky Way has ever eaten, and there's a word for the strange, patient science of reading those trails. It's called galactic archaeology, sometimes near-field cosmology, but I love galactic archaeology, because it's exactly right. These astronomers are archaeologists. They are not digging in dirt. They are digging in starlight. They are looking at the faint arrangement of stars scattered across the sky and reconstructing events that happened billions of years before there was anyone here to see them. Reading the fossil record of our galaxy, not in bones, but in the motions of stars. Now, I've been using soft words. Eaten, absorbed, but let me offer you a slightly stranger frame, because I think it's the truer one, and it's the thread I want to follow all the way through this. Picture the halo of our galaxy not as a quiet graveyard, but as a crime scene. Each one of these stellar streams, each ribbon of stars, is a chalk outline. It marks where a body fell. Something died here, a galaxy, a cluster, torn apart, and its scattered stars are the evidence left behind, still lying exactly where the violence flung them. And the astronomers, our galactic archaeologists, are the investigators walking that scene, kneeling down beside each faint outline and asking the oldest question there is. What happened here? Who was this? And how, when there was no witness, when it all finished before the first human ancestor ever looked up, how could anyone possibly know? That question is the whole story. Hold on to it, loosely as you drift. How do you reconstruct a murder no one saw? But before we get to how we know, let's understand what actually happens. Let's understand how a whole galaxy gets pulled into a ribbon in the first place, because the mechanism is so simple and so gentle that it might just be the most soothing violence in the universe. It comes down to something you already know in your body, even if you've never named it. It comes down to tides, the same reason the ocean rises and falls along the shore. So let me build it slowly. Imagine you're falling. Not frightening falling, just floating down falling, the kind you sometimes feel right at the edge of sleep. And imagine you're falling towards something with a lot of gravity, something enormous, and your feet are pointed toward it, and your head is pointed away. Here's the quiet, strange fact. Your feet are a little closer to that enormous thing than your head is, and gravity gets stronger the closer you are. So your feet feel a slightly stronger pull than your head, just slightly, just the tiniest difference, but it's there. Something is very, very gently trying to stretch you, to pull your feet one way and your head the other. Nothing you'd ever feel in real life, not near anything ordinary. But the effect is real, and it has a name. It's called a tidal force, a tide. It's not one pull, it's the difference between two pulls, the near side and the far side, and that difference is what stretches things. That's what raises the ocean tides on Earth, by the way. The side of the Earth facing the moon gets tugged a little harder than the side facing away, and the whole ocean gets very slightly stretched into a bulge, and the shoreline rises, and later it falls. The moon is not grabbing the water, it's just pulling the near side a hair harder than the far side, and that hair of difference, spread across a whole planet, is enough to move seas. Now take that same idea, that same gentle difference between the near side and the far side, and make it galactic. Our little Sagittarius galaxy is orbiting the Milky Way, and the side of Sagittarius facing in toward the Milky Way's center feels a stronger pull than the side facing out into deep space. There's that difference again. The near side and the far side, and so the whole dwarf galaxy is being very gently, very patiently stretched, not crushed, not exploded. Stretched, drawn out along the line, pointing toward the Milky Way and away from it, like a piece of soft dough pulled slowly between two hands. And the stars on the very edges, the ones out at the front and the back of that stretch, they start to leak away. Because at a certain point, the dwarf galaxy's own modest gravity, its gentle effort to hold its stars together, loses the stretching winds. And the stars at the two ends slip out. They slip out through two particular places, and I love this detail, so let me give it to you slowly. There are two special points, one on the near side of the dwarf galaxy and one on the far side, where the pull of the little galaxy holding its stars and the pull of the big galaxy trying to take them balance out into a kind of open gate. Astronomers call these Lagrange points. You don't need the name. Just picture two doorways, one at the front of the dwarf and one at the back. Two soft openings in the fence of gravity where stars can wander out without ever quite noticing they've left. And here's the beautiful part, the part that turns a leak into a ribbon. Stars leaking out the front door and stars leaking out the back door go to two different places. The stars that slip out the inner door, the one facing toward the Milky Way's center, fall a little closer in. And when you fall closer in toward the center of a galaxy, you orbit a little faster. So those stars race ahead. They pull out in front of the dwarf galaxy, forming a long arm reaching forward along the orbit. We call that the leading tail. The stars running ahead, and the stars that slip out the outer door, the one facing away, drift a little farther out. And when you're farther out, you orbit a little slower. So those stars fall behind. They trail out backward along the orbit, forming a second long arm reaching back the way the galaxy came. That's the trailing tail. The stars falling behind. Two arms, one reaching forward, one reaching back. And the little galaxy in the middle, still holding on, still shedding stars from both doors as it goes. If you could pull back and see the whole thing at once, frozen. You'd see a shape like a long, stretched letter S, or a great sweeping arc drawn across the dark. Not a blob, not a mess. A ribbon, with a leading edge running ahead and a trailing edge falling behind, and the dying galaxy strung along the middle of it like a bead on a thread. That's a stellar stream. That's what wraps our whole galaxy. That's what Ibata and Gilmore and Irwin found in 1994 in the middle of forming. Two tails of stolen stars drawn out through two gravitational doorways, one running ahead and one falling behind, all because the near side of a galaxy feels a slightly stronger pull than the far side. The whole enormous sky-spanning thing comes from that one small difference. Tides, just tides, played out across 100,000 light-years and a few billion years, and I called it violence, and it is, in a sense. A galaxy is coming apart, but notice how gentle it actually is. Nothing is torn in an instant, nothing shatters. Each star simply drifts, one at a time, through an open gate, and joins the ribbon, and keeps on orbiting as if nothing much has happened at all. From the point of view of any single star, there was no catastrophe. It just found itself, over the ages, part of a longer and thinner and lonelier procession than before. The murder, if it's a murder, happens so slowly that no single moment of it would ever look like a crime. Now, here is the question that should be tugging at you, if you're still with me, and not yet gone soft into sleep. If all these stars are just drifting away, scattering off in every direction, then how does the ribbon stay a ribbon? Why doesn't it just disperse into a shapeless fog, a smear of stars going every which way, impossible to tell apart from all the other stars in the sky? Why is there a trail at all, a clean line you could point to and follow, rather than just a blur? And the answer to that is the quiet miracle that makes this whole science possible. So let me give it to you gently, because it's the key to everything that comes after. When the stars leak out of the dying dwarf galaxy, they don't leave in a hurry. They don't get flung. They slip out the two doors, moving at almost exactly the same speed the dwarf galaxy itself was moving. And they slip out onto almost exactly the same orbital path. They inherit the orbit. They keep travelling along nearly the same great loop around the Milky Way that their parent galaxy was travelling. Some just a touch ahead, some just a touch behind, but all of them following essentially the same road. Astronomers have a lovely phrase for this. They say such a stream is dynamically cold. Cold, here, doesn't mean temperature, doesn't mean frozen. It means calm. Orderly, peaceful in its motion. The stars aren't jostling around every which way at wild random speeds. They're all gliding along together in nearly the same direction, on nearly the same path, at nearly the same pace, like a long line of leaves all carried down the very same current of a very slow river. That shared calm is what keeps the ribbon a ribbon. Because they all share the orbit, they stay strung out along that single path for billions of years, a thin, bright thread rather than a scattered cloud. And that, right there, is why any of this can be known at all. Because the stars remember. I have to be careful with that word remember, so let me be honest with you the way I always want to be. Stars don't have memories. They're not thinking of home. When I say the ribbon remembers the galaxy it came from, I mean it as a kind of poetry, and I want you to hear it as poetry, not as fact. But it's poetry pointing at something real. The path itself is the memory. The shape of the stream, the direction all those stars are gliding, the particular loop they trace around our galaxy, all of that is a record. A recording. Because the stars kept the orbit of the thing that made them, the ribbon is a kind of frozen photograph of a galaxy that no longer exists in one piece. The body is gone, but the outline it left, the way its stars still move together along the road it once travelled, that survives. That lingers out there in the dark for ages after the galaxy itself has been pulled to nothing. So when our galactic archaeologists kneel down at that chalk outline, that's what they're reading. Not a static picture, but a motion, a direction, a shared orbit that 1,000 or 1,000,000 stars are all quietly obeying, and that all point back, like arrows, toward a single vanished origin. The stream is dynamically cold, and because it's cold, it's coherent, and because it's coherent, it's legible. You can read it. You can follow the thread back. And think about the timescales here, because this is the part that I find most restful. In a strange way, these streams don't form in an afternoon. A single wrap of a ribbon like Sagittarius, one full loop around the galaxy, takes hundreds of millions of years to trace. Sometimes billions. The whole slow unravelling of a dwarf galaxy plays out over a span of time so vast that a single lap of it can be longer than complex life has existed here on Earth, which means something quietly staggering. No one witnessed these collisions. No one could have. Not because they were hidden, but because they are simply too slow and too old. They were finished, or barely begun, long before there were eyes anywhere on this world to look up. The event you're picturing, a galaxy coming apart into a ribbon over the head of the whole Milky Way, is not a flash, not a crash, not a bang. It's a motion so slow that from where we stand it looks completely still. Frozen. A single held breath that has lasted longer than we have. And here's a small correction I want to make, gently, before you drift off, because you'll hear it said the wrong way everywhere. People love to say the Milky Way eats galaxies, swallows them whole, devours them. And there's a truth in it, but the picture it paints is wrong. And the wrong picture makes the whole thing feel more brutal than it is. Nothing is swallowed whole. There is no gulp. What actually happens is this slow, patient, star-by-star unravelling we've been talking about, playing out over billions of years. The little galaxy doesn't vanish in a bite. It survives, in some smaller and smaller form, for an enormously long time, continuously bleeding stars out its two doors with every long orbit, growing thinner and fainter and more stretched with each pass. Until at last, there's nothing left to call a galaxy, only the ribbon. It's not eating, it's more like a very, very slow dissolving. A thing coming apart in a current so gently that it never quite knows it's coming apart at all. Sagittarius, our starting star for tonight, is right in the middle of that dissolving. It's not gone. It still exists, out there, a battered little knot of stars on the far side of the galaxy, still holding a core of itself together, even now, even as it trails those two enormous arms of lost stars wrapping the entire sky. It has been dying for billions of years, and it is still not finished dying. It has passed through the disk of the Milky Way more than once, each plunge stripping away more of it. And it is still there, still going, still shedding its light in a long, thin line behind and ahead of it. There is something almost peaceful in that, a death so slow it barely registers as death. Just a long, quiet giving away. So that's the picture I want to hand you as we settle deeper into the night. Out there, all around the bright disk of stars we call home, is a vast, dim halo. And that halo is not empty. It is threaded through with these ribbons, these streams. Long, cold, coherent trails of stars, each one drawn out of some smaller thing the Milky Way pulled apart, each one still gliding along the orbit of a galaxy that no longer exists, each one a chalk outline at a crime scene billions of years old. And Sagittarius is only the loudest of them. the most complete, the one wrapped fully around us, more than a whole circle, a galaxy unspooled across the entire sky. We've talked about what happens, the tides, the two doors, the leading tail running ahead and the trailing tail falling behind, the dynamically cold ribbon that stays a ribbon because all its stars share one road. And we've named the strange science of reading these things. Galactic archaeology. Investigators at a scene with no witnesses, kneeling by the chalk outlines, asking who died here and how they could ever know. But we haven't answered that question yet. And it's the good one. It's the one that should be turning over softly in your mind as your breathing slows. If no one saw it, if the whole event is frozen and silent and older than we are, then how, exactly? Does anyone rewind the tape? How do you take a faint band of stars scattered across the night and reconstruct, from that alone, the death of a galaxy that ended before the first fish crawled onto the first shore? There is a way. There's a spacecraft quietly orbiting a still point out in space that has spent years doing almost nothing but measuring, with impossible patience, exactly where the stars are and exactly how they're moving, and with those measurements, astronomers have learned to do something that sounds like magic and is really just very, very careful arithmetic. They've learned to run the clock backward, to take a star gliding along its cold ribbon tonight and calculate where it was 1 billion years ago and 1 billion before that, and watch, in reverse, a galaxy come back together out of its own scattered pieces. But that spacecraft, and how it turned the whole sky into a movie we can rewind, is where we're going next. But before we climb aboard that spacecraft, before we hand the remembering over to a machine, stay here a little longer. Stay at the scene. There's no rush tonight, and the stars aren't going anywhere. They've been where they are for billions of years. They can wait for us to look properly. So let's look. Let's kneel back down beside one of these chalk outlines and really understand what tore the body apart, because the how of it is gentler than the word murder makes it sound. Nothing exploded, nothing was swallowed in a single bite. What happened was slower than that, and stranger, and in its own way almost tender. It was gravity, doing the only thing gravity ever does. Pulling, just pulling, patiently, from one side a little harder than the other. Here's the whole secret of it. When a small galaxy falls toward the Milky Way, the side of it facing us gets pulled a little more strongly than the side facing away. It has to. Gravity fades with distance, so the near side always feels a firmer grip than the far side. It's the same reason the ocean has tides. The moon tugs the near ocean harder than the far ocean, and the water bulges. Now imagine that same lopsided tug, not on water, but on a whole galaxy full of stars. The near stars get pulled forward. The far stars get left behind. And the little galaxy, which used to be a soft round cloud, begins, ever so slowly, to stretch. You could hold your hand up in the dark right now, wherever you're lying, and pull gently at a piece of warm bread dough between 2 fingers, and you'd be doing exactly what the Milky Way does to its meals. One end thins. The other thins. The middle draws out into a strand. And the stars don't snap free all at once. They leak. They slip away, a few at a time, through 2 particular places, 2 quiet points in space where the pull of the little galaxy and the pull of the big one balance out to almost nothing. Astronomers call them Lagrange points. You don't need the name to fall asleep. Just picture 2 soft gaps in a fence, one on the inner side and one on the outer, where the stars can wander out without being flung. 2 openings, and through the inner one, stars drift down toward the center and begin to race ahead. Through the outer one, stars drift out and start to lag behind. That's why a stream has two tails, and not one. There's a leading tail, made of the stars that slipped inward and now run out in front, orbiting a little faster, pulling ahead like the front of a slow procession. And there's a trailing tail, made of the stars that fell out the back and now drag behind. One reaches forward, one reaches back. And the little galaxy sits in the middle, quietly bleeding light from both ends, drawing itself out across the sky into the shape of a long, lazy letter S. A great arc. A ribbon. Not a blob, not a smear, but a line with a direction to it. A line you could almost follow with a fingertip. And this is the part I love. This is the part worth carrying down into sleep with you. Once those stars are out on the ribbon, they don't scatter, they don't drift off in 1,000 directions and lose each other in the dark. They stay together. They stay strung along one single path, one shared road through the galaxy, for 1 billion years and more. Astronomers have a phrase for this. They call the stream dynamically cold, which only means the stars are all travelling calmly, at nearly the same speed, along nearly the same orbit, like a long line of swimmers, all caught in the same slow current. Nobody's thrashing, nobody's darting sideways, they just glide, all together, along the exact path the little galaxy was on when it died. And because they do that, the ribbon remembers. That's the whole reason any of this works. The galaxy is gone. The round cloud of it, the shape of it, the thing it used to be, all of that came apart long ago. But the road it was travelling is still written in the stars it left behind, because those stars are still on that road. The stream is a recording, a dropped thread that traces, star by star, exactly where the vanished galaxy once walked. It's a memory made of light, hanging in the dark, waiting for someone to read it. Now, I should be careful and honest with you here, because it's the kind of thing worth being honest about even half asleep. When we say the galaxy remembers, that's a lovely thing to say, but it's a poem, not a fact. The stars don't feel anything. They don't know they were once part of something. It only looks like memory, because the physics is so faithful, so patient, that the pattern survives long after the thing that made it is gone. And honestly, that might be the more beautiful version anyway. Now hold in your mind, just for a moment, how big this actually is. The most dramatic of these ribbons belongs to a little galaxy called the Sagittarius Dwarf, and it is being torn apart right now, tonight, as it plunges again and again through the disk of our galaxy. Its stolen stars have been pulled out into a stream so long that it doesn't just reach across the sky. It wraps all the way around, more than 360 degrees. A complete loop. One small galaxy, unspooled into a single band of stars that circles the entire Milky Way, longer than our whole galaxy is wide. If your eyes were tuned to see it, you could stand in a field on a dark night and watch the remains of another galaxy arc clear over your head and down the far side of the world. And if you're enjoying drifting through this with me, a quiet like or a subscribe genuinely helps this small channel keep going. No pressure. And while you're lying there, I'd love to know, softly, where in the world are you listening from tonight? Which corner of the sky is over your roof right now? Because that same great loop of stolen starlight is up there above every one of us. Unnoticed, unhurried, wrapped around the sky like a ribbon somebody tied a very long time ago and never came back to untie. So, the question that's probably drifting through your mind right now, somewhere between awake and not quite, is a very reasonable one. How? How does anyone actually know any of this? How do you look up at the night sky and read, in those faint, scattered points of light. The story of a galaxy that was eaten billions of years before you were born? How do you reconstruct a collision that no human and no ancestor of any human ever witnessed? It seems like the kind of claim that should require some extraordinary evidence. And it does. And the evidence, when you actually look at it, is more extraordinary than the claim. Let's start with what we had before the revolution, before the instrument that changed everything. It's the year 2006. A collaboration of astronomers is working with data from something called the Sloan Digital Sky Survey, an enormous systematic effort to photograph a huge swath of the sky in extraordinary detail and build a catalogue of everything it could see. Millions of stars, millions of galaxies, catalogued and measured. And when a group of researchers sat down with all of that data and started looking very carefully at the faint outer halo of the Milky Way, not the bright disk, but the dim, diffuse sphere of old stars surrounding it, they noticed something remarkable. Something that looks, when you see the image, almost unbelievable. They published what they called the field of streams, and the name is exactly what it sounds like. In this image of the northern sky, stitched together from the survey's data, you can see not one ribbon of stars, but several. Arcs and bands crossing and overlapping each other, draped across hundreds of square degrees of sky like creases in old fabric. There is the great sweep of the Sagittarius stream, its leading and trailing arms ghosting across the field. There is a thinner, fainter thread now called the Orphan stream, wandering across the picture with no obvious source. And there are other structures, partially understood, partially mysterious, all of them hovering in that dim outer halo, all of them whispering that the history up there is complicated, layered, old. This image was a proof of concept, a demonstration, visible to the eye, that the halo really is threaded, that these ribbons aren't theoretical constructs or simulation artifacts. They are there. Real overdensities of real stars, in real patterns, in a real sky. And yet, and this is the limitation of a photograph, seeing that they are there and understanding what they are doing are two very different things. A photograph gives you a position, it gives you brightness, but it doesn't tell you how fast a star is moving, or in which direction, or how far away it truly is. It gives you one moment frozen in time, a single frame from a film that has been running for 10 billion years. To read the story, you don't need a photograph, you need a movie. And to make a movie of the stars, you need to know not just where things are, but how they're moving. All three dimensions of position, all three dimensions of velocity. And that, for most of human history, was genuinely out of reach. Enter Gaia. Gaia is a spacecraft built by the European Space Agency. It launched in December of 2013 and settled into orbit around what's called the L2 point, a gravitationally stable location roughly 1.5 million kilometers behind Earth, on the side facing away from the Sun. From there, it has a clear, unobstructed view of the entire sky. And it has been watching, measuring, cataloguing for years. What Gaia does, in plain terms, is measure where stars are with almost unimaginable precision. It spins slowly, sweeping its two telescopes across the sky again and again, building up a detailed record of each star's position not once, but many times. From those repeated measurements, it extracts two things. First, parallax, the tiny apparent shift in a star's position as the Earth moves around the Sun, which tells you, with geometry alone, how far away the star actually is. And second, proper motion. the slow drift of a star across the sky over time, the way a very distant plane seems to move slowly across your field of view. Measure that drift precisely enough, and you know how fast the star is moving across your line of sight. How precisely? This is the part that is genuinely difficult to hold in your head. Gaia's astrometry, the formal word for the measurement of stellar positions, operates at the micro-arcsecond level. A micro-arcsecond is 1/1,000,000th of an arcsecond, which is itself 1/3600th of a degree. To give you some grip on that number, it is equivalent to detecting the angular width of a single human hair held up at a distance of roughly 1,000 kilometers. Not a meter, not a kilometer, 1,000 kilometers. And Gaia does this routinely. For nearly 2 billion stars, not a few dozen, not a few million, close to 2 billion individual points of light, each one measured with a precision that would have been laughable to suggest a generation ago. The result of all of this watching and measuring is something that has genuinely changed astronomy. Gaia turned the sky from a static picture into something close to a film. A map not just of where stars are, but of where they're going. And that is a fundamentally different kind of knowledge. Because if you know where something is, you have a snapshot. But if you know where something is, and where it's heading, at what speed, in what direction, then you can run the arithmetic backwards. You can ask, where was it 1 billion years ago? And the mathematics, as long as the gravity model is good enough, will tell you. That is how you replay a murder nobody witnessed. But here's where it gets just a little more complicated, and stay with me because it matters. Knowing where a star is going requires knowing all 3 dimensions of its velocity. Gaia gives you 2 of them beautifully, the 2 dimensions of motion across the sky, the proper motion, the slow sideways drift. What Gaia doesn't measure directly, for most stars, is the radial velocity, the speed at which the star is moving toward you or away from you along the line of sight. And that third number is crucial. Without it, you have an incomplete picture. You know how a star is moving across your field of view, but not whether it's rushing toward you or receding. You're missing one axis of the 3-dimensional truth. This is where teams of ground-based astronomers come in, patient and persistent, spending thousands of hours at telescopes around the world. The Southern Stellar Streams Spectroscopic Survey, known simply as S5, the Apache Point Observatory Galactic Evolution Experiment, APOGEE, the Dark Energy Spectroscopic Instrument, DESI. These surveys point their instruments at stars in and around the known streams and measure something called a radial velocity by examining the spectrum of the starlight, the way specific colors are shifted slightly toward red or blue, depending on whether the source is moving away from or toward you. It's the Doppler effect, the same reason a passing siren changes pitch, but applied to light instead of sound. And that radial velocity, that one last number, completes the picture. Now you have 6 numbers per star. 3 coordinates in space telling you exactly where it is in the 3-dimensional galaxy. 3 components of velocity telling you exactly how it's moving through that 3-dimensional galaxy. And 6 numbers, fed into a sufficiently good model of the Milky Way's gravity, are enough. Enough to run the clock backward. Enough to reconstruct the path the star has been traveling, not for years or centuries, but for billions of years. Enough, in principle, to trace it back to a moment before the stream existed, when it was still orbiting inside the galaxy that is no longer here. It requires one more ingredient, of course. You need the gravity model, a mathematical description of the Milky Way's total gravitational pull at every point in the galaxy, accounting for the disk, the central bulge, the gas, the stars, and the vast invisible dark matter halo enveloping all of it. Getting that model right is genuinely hard, and it's a problem the science is still working on, still refining with each new stream measurement. But the point is this: backward orbit integration is not speculation. It is clockwork. You take the current position and velocity of a stream star, you apply the known laws of gravity, you run the equations in reverse, and you get a trajectory, a history, a forensic record. Now, imagine doing that not for one star, but for thousands, or tens of thousands. You take all the stars in a given stream, all of them with their 6 number files completed, and you integrate them all backward through the same model of the galaxy's gravity. And if they truly belong together, if they were once part of the same dwarf galaxy or the same star cluster, then as you rewind time, those stars should converge. They should pull back together, collapsing in reverse toward the thing that they came from. You are literally watching, in the mathematics, a galaxy reassemble. You are watching the Milky Way eat its meal. And then there are the simulations. N-body simulations is the name, and what they involve is building a virtual version of the lost object, a dwarf galaxy, a globular cluster. Whatever the stream seems to describe, as a collection of thousands or millions of point masses, each one representing a parcel of stars or dark matter. You set them up in the model of the Milky Way's gravity, you start the clock running, and you let the physics play out. The virtual dwarf begins to be torn apart. Stars leak from the Lagrange points, 2 tails extend. The ribbon stretches. The simulation creates a synthetic stream. And then you compare. You lay the synthetic stream over the real one, and you ask, does it match? Does the length match? The curvature? The width? The density? If not, you adjust the model. Change the mass of the galaxy, change the concentration of the dark matter halo, change the starting orbit, and you run it again. You iterate, again and again, until the simulation reproduces what you actually observe. And when it does, you have something remarkable, not just a description of what is, but a reconstruction of what was. The mass of the destroyed galaxy, the shape of the halo's gravity, the history of a collision that nobody alive, or ever alive, had any hope of seeing with their eyes. Before the next stretch of our journey, I want to mention something quickly. After years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. But here's where it gets strange, and this is the part that tends to make astronomers quiet for a moment when they think about it clearly. All of those methods, all of that machinery of precision and simulation operate on a simple and initially surprising assumption that the stars in a stream remember where they came from, not literally, but in the most physical sense, because when a star is part of a stream, it shares an orbit. It follows essentially the same path through the galaxy as all its siblings, the other stars from the same destroyed object. And even though billions of years have passed, even though the stream has stretched and precessed and wound itself around the galaxy, that shared orbit persists. The stars have been drifting apart, yes, slowly, over immense stretches of time. But they haven't randomized. They haven't mixed in with the background. They are still, in the language of orbital mechanics, coherent. They form what's called a dynamically cold structure, which means they haven't been jostled and scattered into chaos. Their velocities are similar. Their paths are similar. And that similarity is enough. Chemistry adds a second layer of memory, deeper than motion. And this is one of the most quietly elegant ideas in the whole field. Stars that were born together, that condensed from the same cloud of gas inside the same dwarf galaxy, carry the same chemical fingerprint, not quite the same element by element, because there is always some variation, but the same broad ratios. The ratio of iron to hydrogen, the ratio of magnesium to iron, the proportion of elements heavier than iron produced in the specific kinds of stellar explosions that occurred in that particular galaxy. Every galaxy has its own history of star births and deaths, its own particular enrichment pattern, and those patterns get baked into the stars that form there. They are, in a very real sense, passports, chemical passports from a country that no longer exists. So even if a stream has dispersed so thoroughly that its stars are too spread out to form a visible ribbon in the sky, even if the motion signal is too faint to isolate with confidence, the chemistry may still give it away. You take a spectrograph to a field of stars that looks thoroughly random, and you discover that a dozen of them share an unusual iron to magnesium ratio that marks them as coming from outside the Milky Way. And suddenly you have identified siblings who didn't know they were related. The analogy to DNA testing isn't even much of a stretch. You are matching chemistry at a crime scene, decades and billions of years after the event. Astronomers call this chemical tagging, and it opens up a future for galactic archaeology that is genuinely exciting to think about even as you're drifting towards sleep, because it suggests that even the most ancient and dispersed debris, the meals so thoroughly digested that the physical ribbon is long gone, might still be detectable in the chemical record. The galaxy keeps these receipts, not intentionally, not because anyone designed it to, but because the physics is patient, because nuclear burning follows rules, because stars, once formed with a particular ratio of elements, carry those ratios with them to the end of their lives and beyond. And then there is one more clue, perhaps the most elegant of all. The smoking gun that doesn't require any chemistry or any careful parallax measurement, that you can see in a broad statistical sense just by looking at which direction things are moving. Our Milky Way's disk rotates. If you could look down on it from above, you would see a great flat spiral turning one way, all the stars and gas and dust of the disk moving in roughly the same direction, circling the galactic center in a grand ordered procession. The sun goes around that way. The nearby stars go around that way. The spiral arms are tracing that same rotation. And if you were born inside this galaxy, formed from a cloud of gas that was already part of that rotating disk, that is almost certainly the direction you are moving. Because the rotation is what the gas was doing. The rotation is inherited. But if you come from outside, if you were a star in a dwarf galaxy that fell in from a particular direction, at a particular angle, with its own rotational momentum that had nothing to do with the Milky Way's spin, then you might be going the other way, orbiting in the opposite direction to the disk. Retrograde. And retrograde orbits in the Milky Way are a red flag. Not in every individual case, there are always exceptions and complications, but statistically, a large population of stars moving in the backward direction relative to the disk is almost impossible to explain if those stars formed inside the Milky Way. They are, almost certainly, foreigners, donated stars from a swallowed galaxy. The backward motion is the smoking gun. It says, I did not start here. I came from somewhere else, and my adopted galaxy is spinning in a direction that has nothing to do with where I began. This retrograde signal, combined with chemical tagging and the stream morphology and the backward orbit integration, gives astronomers multiple independent lines of evidence pointing toward the same conclusions about the galaxy's history. No single line of evidence is perfect. Each has its uncertainties, its ambiguities, its model dependencies. But when they all agree, when the chemistry matches the motion, matches the stream geometry, matches the simulation, the reconstruction becomes very hard to argue with. The forensic case becomes, in the language of science, robust, and the tools for all of this have been getting better year by year. Gaia's data releases have come in stages, each one richer and more precise than the last, each one extending the catalogue to fainter stars, to more distant reaches of the halo, to more complete 6-number files for more of the streams. The ground-based surveys are going deeper. The computational power available for N-body simulations is growing. The gravity models are being refined. It is worth pausing for just a moment, lying there in the quiet, to appreciate what it means that this is possible at all. We are here, on this one small planet, orbiting one ordinary star, embedded in the middle of a galaxy so large that light takes 100,000 years to cross it. We cannot step outside and look at it from above. We cannot go back in time. We cannot watch the collisions happen. We are, in a very real sense, inside the evidence. We are inside the crime scene. And yet, with instruments precise enough to measure the angular width of a hair from 1,000 kilometers away, with mathematics that can run gravity backward through billions of years, with spectroscopes that read the chemical biography of individual stars, we have managed to reconstruct events so ancient that the word ancient barely does the job. Events that were finished, in some cases, before the Earth was formed. That is what Gaia made possible. That is what the 6 numbers per star unlocked. Not just a catalogue, a confession. A slow, careful, extraordinarily detailed confession extracted from 2 billion points of light scattered across the sky, each one a witness to something enormous that happened a very, very long time ago. And the SDCC's field of streams, that image from 2006, was the first moment the full extent of the gallery became visible. The first time you could look at a picture of the sky and see the layered, overlapping ribbons plainly, undeniably there, writing their ancient history across the northern sky. Not one stream, several, crossing each other, each one a separate story, a separate meal, a separate collision reconstructed from the wreckage. The image was, in the truest sense, a map of the galaxy's past. We just didn't yet have all the tools to read it properly. What Gaia did was give us the reading glasses, and with those reading glasses, the reading has only grown richer. Because once you have the tools, the precision, the 6 numbers, the chemistry, the simulations, you can start applying them everywhere. You can sweep through the whole catalogue and ask which groups of stars share the same orbit, which populations carry the same chemical fingerprint, which clumps are moving backward in quiet defiance of the galactic spin. And the answers come back layered and various and deeply strange. Because it turns out the galaxy has not just 1 or 2 or 3 stolen histories stitched into it. It has dozens, perhaps many more. Each one a separate chapter in the biography of a galaxy that grew, in part, by taking. And right now, tonight, the reconstruction is still being written. More data coming from the ground-based surveys, more stars with complete 6-number files, more simulations running on the computers. The forensic case for each identified merger is ongoing. New streams are being found. Old streams are being traced farther, and the picture that is assembling itself slowly in the data is stranger and more layered and more violent in its ancient past than anyone looking at the calm, beautiful Milky Way on a clear night would ever easily imagine. Let the sky be outside your window or simply in your mind. The ribbon of the Sagittarius stream is up there, unlit by any human eye, wrapped all the way round the world above you. And somewhere in the same darkness are dozens of other trails, fainter, older, their constituent stars mixed and tangled with other tales of disruption. The whole halo, that dim sphere surrounding the bright disk you might know as the Milky Way on a dark summer night, is a palimpsest, a surface on which old text has been written over and over again by the ongoing work of gravity and time. And we have, with enormous ingenuity and patience, learned to read it. That, in itself, is worth a quiet moment of something like amazement. So, the catalogue of what we have found. The named meals, the identified remnants of galaxies and clusters that no longer exist as such, but whose stars are still here, still moving, still carrying their chemical and dynamical testimony through the outer reaches of our galaxy. If you're comfortable, let's drift through them one by one. Each is a world, or rather, once was a world, a galaxy, a collection of millions or billions of stars with its own history, its own gas clouds, its own stellar generations, and each is now a thread of evidence. The deepest chapter, the one that goes back the farthest and changed the Milky Way the most profoundly in a single event, was identified not from a stream on the sky, but from a peculiar clustering of velocities that showed up in the Gaia data with a distinctive shape. Not a ribbon, a blob, an elongated radial smear in the space of stellar velocities, stars moving in highly eccentric orbits, plunging in toward the galactic center and then shooting back out like comets on very stretched ellipses. When astronomers plotted these stars in what's called velocity space, they formed a sausage shape. And the event that produced them was given the name Gaia-Enceladus, honoring both the spacecraft that revealed it and the Greek myth of the giant, a massive entity that was, in the end, subdued and buried. Gaia-Enceladus was not a small galaxy. Current estimates suggest it was comparable to the Milky Way's own mass at the time of the merger, which is saying something. The collision with Gaia-Enceladus was, according to the reconstructions, one of the most transformative events in the Milky Way's history. It happened somewhere in the range of 8 to 11 billion years ago, deep time, before the Earth existed, before the Sun existed, before most of the stars in our galaxy's disk were formed. And when this galaxy came in, it came in hard and in a roughly radial direction. Not a gentle sideways glancing blow, but something closer to a head-on plunge. The resulting debris, the stars that survived the merger and were mixed into the Milky Way's halo, make up what is now sometimes called the Gaia sausage. And the evidence, the elongated radial orbits, the distinct chemical signature different from the disk's native stars. The sheer number of them spread through the inner halo, all of it points to one conclusion: a large fraction of what we call the stellar halo, that diffuse sphere of old stars surrounding the disk, was built from the body of this one enormous meal. Gaia-Enceladus was not a snack. It was, in some sense, the main course. And the Milky Way we live in today is different because of it. And that raises a question worth sitting with for a moment. How do we actually know any of this? How do you look up at the sky, at the vast and apparently static scatter of points of light and conclude that a galaxy was swallowed 8 billion years ago and that its debris is right there, orbiting in particular directions with particular speeds, carrying a particular chemical memory. How do you read a crime scene when the crime happened before the Earth was born? The answer, mostly, is a spacecraft called Gaia. Gaia was launched by the European Space Agency in December 2013. It sits at a gravitationally stable point in space called L2, about 1.5 million kilometers beyond Earth, slowly scanning the entire sky. And what it does, in the simplest terms, is measure stars. Not just their brightness, not just their colors, but their positions, with a precision that, when you first encounter it, seems like it must be an error. Gaia can measure the apparent shift of a star to an accuracy of a few micro-arc-seconds. If you find that number abstract, here is what it means in practice. Imagine a single human hair held upright, seen from roughly 1,000 kilometers away. That is the angular size Gaia can distinguish. That is the scale of the differences it is tracking, written across a sky full of 2 billion stars. 2 billion. Nearly 2 billion individual stars, each measured not just as a point of light, but as an object with known position and known movement. Because Gaia does not take a single picture. It scans, and scans again and again over years, and in the differences between those scans, the tiny, patient shifts of each star across successive passes, it builds up what amounts to a three-dimensional map of the galaxy in motion. Not a photograph, a film. A very long, very precise film, frame by frame across years of observation, in which you can watch the stars move and from their movement reconstruct where they have been. But here is where it gets a little more complicated and a little more interesting. Gaia gives you 5 of the 6 numbers you need. For each star it measures 3-dimensional position and 2 components of motion across the sky, what astronomers call proper motion. That is enormously useful. But to complete the picture, to know exactly how a star is moving in 3 full dimensions rather than 2, you need one more thing, the radial velocity, which is how fast the star is moving directly toward you or directly away from you. And Gaia, for most stars, can only estimate that. The 6th number often has to come from somewhere else. That somewhere else is a collection of ground-based spectroscopic surveys, projects with names like S5, the Southern Stellar Stream Spectroscopic Survey, and Apogee and DESI. These surveys point large telescopes at carefully chosen stars and measure the tiny shift in the wavelengths of their light caused by their motion along the line of sight. A star moving toward you compresses its light slightly toward the blue end. One moving away stretches it toward the red. The shift is tiny, but it is measurable, and it gives the 6th number. Position, 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 velocity, velocity, velocity. 3 spatial coordinates, 3 velocity components. A complete forensic file for each star. With 6 numbers for a given star, something remarkable becomes possible. You can run the clock backward. The galaxy's gravitational field, the way the total mass of the Milky Way, dark matter and stars and gas and everything else, curves and pulls across space, can be modelled. It is a difficult model, an approximation, but it is a principled one, built from decades of observations. And once you have that model of the gravitational field, and once you have the position and velocity of a star right now, you can ask the model, if the physics have been consistent, where was this star 1 billion years ago? 2 billion? 8 billion? You integrate the equation of motion backward in time, like rewinding a recording, and the star traces a path back through the model galaxy. You replay the crime. To check the replay against reality, you run something called an N-body simulation. You take a virtual version of the destroyed dwarf galaxy, a cloud of thousands or millions of simulated particles, each one representing a clump of stars, and you drop it into the model Milky Way. You let it orbit and get pulled apart. You watch the simulated stream form, the two tails unfurl, the debris spread along the orbit. And then you compare the simulated debris to the real stars you have observed. You adjust the model. You rerun the simulation. You keep going until the shape of the virtual stream matches the shape of the real one. When it does, you have your answer. You know within the uncertainties the models carry, what the original galaxy weighed, what orbit it was on, when it fell in, and what happened to it. But there is a chapter before Gaia, and it deserves a moment. In 2006, a survey called the Sloan Digital Sky Survey produced an image of a large patch of the northern sky, built up from years of careful photographic data. And when astronomers looked at the distribution of faint stars in that image, not individual stars, but the statistical texture of the density, the places where stars were slightly more crowded than elsewhere, they saw rivers. Not literal rivers, of course, but ribbons and arcs of slightly elevated star density draped across the sky in overlapping curves and folds. They named the image the Field of Streams. It was the first visual proof that the outer halo was not smooth, not empty, not uniform. It was threaded. It was full of the trails of things that had been destroyed there. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. But here is where it gets stranger. Because the streams are not just beautiful. They are forensic evidence in a second, more intimate sense, not just of orbit and origin, but of chemistry. And the chemistry, it turns out, is as distinctive as a fingerprint. Stars form together in a cloud of gas, and they inherit the elemental composition of that cloud. The ratios of iron to magnesium, of europium to barium, of one element to another. These reflect the particular history of nucleosynthesis in the region where the star was born. What heavy elements had already been forged by earlier generations of stars, and in what proportions a star born inside the ancient Milky Way carries one fingerprint. A star born in a dwarf galaxy orbiting elsewhere, a smaller and slower place where the chemistry evolved differently, carries another. The fingerprints do not match. And they do not fade. Billions of years later, the stars still carry their original chemical signatures intact, woven into the spectra of their light, readable by a spectrograph on a ground-based telescope. This is called chemical tagging. And combined with the orbital information from Gaia, it allows astronomers to do something that sounds almost impossible. To look at a star currently orbiting inside the Milky Way's halo and say, with genuine confidence, that star did not form here. It was donated. It arrived as part of something else, something that no longer exists. One of the clearest signatures of foreign origin is motion. Our galaxy's disk rotates. Stars born in the disk orbit, in the same general direction as each other, and as the disk itself, but stars delivered by an infalling dwarf galaxy, a galaxy that came in on its own orbital path, which may have had nothing to do with the Milky Way's internal rotation, can end up orbiting backward. Retrograde, astronomers call it. moving in the opposite direction to the disk's rotation, against the general flow, like swimming upstream in a current you were never part of. That retrograde motion is a smoking gun. A large population of stars sharing a retrograde orbit and a common foreign chemistry is not an accident. It is a galaxy that was here, that orbited and was pulled apart, and whose stars are still tracing the memory of that original path, moving against the grain of everything around them. And that retrograde motion has been the key that unlocked some of the most significant discoveries in all of galactic archaeology. Because when astronomers took the full Gaia catalogue and began sorting through its hundreds of millions of stars, filtering for those orbiting in the wrong direction, filtering for that distinctive foreign chemistry, they found something they hadn't expected to find so close to home. They found a ghost, not a faint whisper at the edge of the sky, something enormous, something that, once they saw it, was undeniably there, millions of stars on elongated radial orbits. Stars that don't loop comfortably around the galactic center the way disk stars do, but instead plunge deep in and then swing far back out over and over like the pendulum on an old clock. Long stretched orbits, back and forth, back and forth. Stars going inward toward the bright crowded center and then out again, and then in again, tracing paths that look, when you plot them in velocity space. When you map not where the stars are, but how fast they're moving and in which direction, like a long oval smear. A sausage. That's actually what astronomers called it. The Gaia sausage. The more formal name is Gaia-Enceladus. And it is the fossil record of one of the most important things that ever happened to our galaxy. Somewhere between 8 and 11 billion years ago, when the universe itself was only a few billion years old, when Earth did not yet exist, when the sun had not yet ignited, the young Milky Way encountered another galaxy. Not a tiny thing. A substantial dwarf galaxy, massive enough to contribute billions of stars to our halo. Massive enough that its arrival fundamentally changed the structure of the galaxy we live in today. The two merged. The smaller galaxy, Gaia-Enceladus, was pulled apart and absorbed. Its stars did not vanish. They were incorporated. They were folded into the Milky Way like an ingredient into a batter, and they are still here, still moving. Still carrying the memory of that original infall in the shape of their orbits. What those elongated radial paths tell astronomers is that this galaxy came in nearly head-on. It didn't graze the Milky Way sideways on a gentle curved trajectory. It dove in deep, plunging through, and the gravitational interaction scrambled its stars onto those long back-and-forth pendulum orbits. The sausage shape in velocity space is the signature of that particular kind of violent, near-direct infall, and it is spread through a large fraction of the inner stellar halo. When you look at the stars relatively close to the Sun that belong to the halo rather than the disk, many of them, perhaps the majority, are immigrants from Gaia-Enceladus. Not born here. Donated. Amina Helmi's name appears often in this story. She was among the astronomers who helped identify and characterize Gaia-Enceladus, and her work is woven through the history of galactic archaeology in a way that goes back even further. In 1999, well before the Gaia mission launched, well before anyone had the full 6-number catalogue of stellar positions and motions that would become the foundation of this field, she and her colleagues identified something remarkable while studying a smaller sample of halo stars. They found a group of stars near the Sun, not physically close, orbiting in the same general region of the halo, that shared a distinctive looping motion. Stars with a particular combination of angular momenta, a particular way of swinging through the galaxy that identified them as siblings. Not siblings by proximity, siblings by origin. These became known as the Helmi Streams, and they are the remnants of a dwarf galaxy that fell into the Milky Way somewhere between 6 and 9 billion years ago. A galaxy that was already old when it arrived, a galaxy that has been gone for so long that nothing of its original shape remains. No visible core, no defined structure, just these stars continuing to orbit in ways that betray where they really came from. The Helmi Streams were one of the first merger events ever successfully reconstructed from stellar motions alone, before Gaia existed, before anyone could measure positions and velocities for billions of stars at once. A proof of concept for an entire discipline. And then there is Sequoia. If Gaia-Enceladus came in deep and fast, Sequoia came in differently. The evidence for Sequoia comes from a distinct population of stars found on retrograde orbits, those backward swimmers again, but with a chemical signature distinct from the Gaia-Enceladus debris. Different metallicities, different elemental ratios, a different kitchen, you might say, where the stars were cooked. Sequoia is thought to have been a separate dwarf galaxy, a separate meal, in falling on a retrograde trajectory and contributing its own population of stars to the halo. The orbital paths are real. The chemical distinction is real. The case for Sequoia as a separate event, rather than a part of Gaia-Enceladus, rests on those two lines of evidence running in parallel. And then there is something older still. Something that astronomers are still actively arguing about, which is itself a sign of how deep the archaeology goes. There may have been an earlier major merger than Gaia-Enceladus, one that happened at a time when the Milky Way was so young that it barely had a disk, so early that the structures it helped build are buried in the innermost parts of the galaxy, overwritten and compressed by everything that came after. This event is sometimes called Kraken, sometimes Heracles. Different research groups have proposed it from different lines of evidence, and whether they refer to the same merger or different ones is still being sorted out. The evidence comes primarily from studying the ages and orbital properties of globular clusters, those dense, ancient balls of stars we mentioned earlier, scattered through the halo. Some globular clusters appear chemically and dynamically consistent with having arrived already formed inside an infalling dwarf galaxy, rather than forming inside the Milky Way itself. The statistics suggest that a very massive, very early merger may have helped build the inner halo and even influenced the formation of the galaxy's central bulge. Treat this as a leading reconstruction, not a settled verdict. The astronomers working on it will tell you the same thing. The evidence is real. The interpretation is still being tested, the merger's precise identity and mass still genuinely debated. But the fact that it is being seriously investigated, the fact that there are globular clusters carrying the chemical memory of a galaxy that has otherwise left almost no trace, that is itself extraordinary. The galaxy's earliest meal, faint as a rumour, preserved only in the orbital biographies of a few hundred ancient star clusters scattered through the halo. Now, let's go a different direction. Let's talk about an orphan. For years, astronomers cataloguing stellar streams in the sky came across a particular trail of stars that didn't fit. A stream, real and measurable, arcing across a significant patch of sky, but with no obvious parent object. No dwarf galaxy, no globular cluster in the vicinity that could have produced it. Its origin was genuinely unknown. And so it was called, simply and honestly, the Orphan Stream. A trail of stars with no family anyone could name. The Orphan Stream has since been linked to a region associated with the Gruz-2 dwarf galaxy, though the connection is still being studied and refined. It is now sometimes called the Orphan-Chenab stream, the Chenab name coming from a river. Part of the naming tradition we'll come to in a moment. But the more visually striking thing about the Orphan Stream is not where it came from. It's what happened to it. If you plot the Orphan Stream across the sky and compare where it is to where a smooth, undisturbed stream ought to be if it were orbiting in a simple, symmetric galaxy, something is wrong. The stream is kinked, bent, wobbling off the path it should be on, as if something huge and nearby reached out and tugged it sideways. And something did. The same massive neighbours responsible for the Magellanic Stream, which we'll get to, are also responsible for the Orphan Stream's wobble. The Large Magellanic Cloud, not a small thing, a galaxy in its own right, massive enough to have its own gravity. Currently in the process of its own complicated infall toward the Milky Way, is massive enough to perturb the orbits of streams that pass near it. Its gravitational influence is not subtle. The Large Magellanic Cloud doesn't just get pulled by the Milky Way, it pulls back. It bends streams. It makes the galaxy slightly lopsided, off balance. Dynamically asymmetric in ways that astronomers now have to account for when they build their models. The Orphan Stream's kink is a measurement in a way. A record of where the Large Magellanic Cloud was when the stream passed near it. Another line in the forensic file. But not all of the streams in the halo come from dwarf galaxies. Some of them, the thinner, more delicate ones, the ones that look like a single thread of silk rather than a broad river, come from globular clusters. And they tell a slightly different kind of story. Palomar 5, sometimes just called Pal 5, is one of the most famous examples. Pal 5 is a globular cluster in the process of being torn apart. Not finished. Still happening, the cluster itself still exists, a loose, sparse collection of stars that has clearly been heavily eroded by the Milky Way's tides, but trailing from it, on both sides, are tidal tails stretching tens of thousands of light-years. A leading tail and a trailing tail. The two-armed structure we talked about earlier, the Lagrange point mechanism, the stars leaking out through those two gravity gates. Pal 5 shows it in real time. You can look at it. The stream is there, measured, mapped, and the cluster at its centre is clearly running out of stars to lose. What makes Pal 5 and streams like it valuable as scientific instruments is exactly the thing that distinguishes them from dwarf galaxy streams like Sagittarius. Globular clusters have no dark matter of their own. They are purely stellar objects, stars and the gravity those stars create together, nothing else. Without a dark matter halo to puff them up and give them extra internal gravity, the stars that leak out are tightly constrained. The stream they form is cold and thin, dynamically, in the way that phrase means in astronomy, the stars aren't scattered widely in velocity. They are closely bunched together, moving in nearly the same way, at nearly the same pace. A cold, thin stream is a more sensitive instrument. It quivers more easily. The faintest perturbation leaves a visible scar. And then there is the Phoenix stream. The Phoenix stream is the remnant of a globular cluster, and not just any cluster. When astronomers measured the chemistry of its stars, they found something that stopped people in their tracks. The stars are nearly chemically pure. What that means is that they contain almost no heavy elements. Elements like iron, like calcium, like the things that get forged in generations of stars and spread through a galaxy over time as stars age and explode and seed the next generation. The Phoenix Streams stars barely have any of that enrichment at all. They are close to the original material of the universe, mostly hydrogen and helium, with only the faintest trace of anything heavier. This is extremely unusual, and it matters for a specific, puzzling reason. Globular clusters, this chemically pure, this old, this pristine, are thought to have been among the very first structures to form after the Big Bang, when the universe was young and heavy elements were nearly absent. But there is a theoretical problem. There appears to be a lower limit to how massive a globular cluster can be and still form and survive, and the cluster that produced the Phoenix Stream, based on how many stars remain in the stream, appears to have been smaller than that theoretical minimum. Lighter than the floor. A cluster that, according to our models, shouldn't quite exist. The stream preserved the evidence of it. Without the stream, without those stars strung across the sky, still carrying their chemical fingerprints from before the Milky Way was fully formed, we wouldn't know this cluster had ever been there. The stream is the only record. And the record says something we don't fully understand yet. Now, the Magellanic Clouds. You can see them with your naked eye if you live in the southern hemisphere, or if you are somewhere dark enough and far enough south. Two smudges of light in the night sky, like detached fragments of the Milky Way, satellites trailing alongside our galaxy. The large Magellanic Cloud and the small Magellanic Cloud, dwarf irregular galaxies, active with star formation, not the old and faded relics of an early universe, but vigorous and ongoing places where new stars are being born right now. They are being pulled inward. Their orbits are bringing them gradually closer to the Milky Way, and the Milky Way's gravity is already working on them, already beginning the process of tidal disruption that eventually disassembles everything that comes too close. The evidence for this is directly visible in the sky, and it is called the Magellanic Stream. Unlike the stellar streams we've been talking about, ribbons of stars, old and cold and slow, the Magellanic Stream is primarily a ribbon of gas. Hydrogen gas, stripped from the Magellanic Clouds by the same tidal forces that shred stars from dwarf galaxies, trailing behind them and stretching ahead of them as they move. It spans more than 100 degrees of sky. An enormous gaseous ribbon, the Milky Way's gravity reaching out and peeling material away from two galaxies that are not yet consumed, not yet dismembered, but already being prepared. The Magellanic Clouds are future meals, in a sense, meals being slowly arranged on the table. But they are also massive enough, particularly the large Magellanic Cloud, that they are not passive objects waiting to be absorbed. They are actively affecting the galaxy around them right now, bending streams, pulling on the dark matter halo, making the whole system dynamically complicated and lopsided. A galaxy absorbing another is not a one-way interaction. The Eton pushes back, however briefly. And out beyond the individual named streams and the famous bright clouds, there is a growing world of fainter, quieter threads. The Southern Stellar Stream Spectroscopic Survey, a collaboration of ground-based telescopes, known by the abbreviation S5, has spent years specifically targeting and characterizing stellar streams in the southern sky, adding the crucial piece that Gaia alone cannot provide, radial velocities and chemistry, measured one star at a time through spectroscopy, completing the forensic file that positions and proper motions begin. And what S5 found, and continues to find, is that the halo is more threaded than anyone had suspected. The streams they've catalogued carry names from rivers. Jhelum, a river in Pakistan and India. Indus, one of the great rivers of South Asia. Atlas, after the telescope survey that first found it. Ravi, another river of the Punjab region. Elqui, a river in Chile, from whose clear desert skies many of these observations are made. Alika Uma, Turunbura, Wilka Yaku, whose name comes from Quechua and means sacred water. These are all real streams, all real ribbons of stars, strung through the galaxy's halo, each one the dispersed remnant of a star cluster or a small dwarf galaxy that came too close and was pulled apart. Each one a record of a collision, each one still moving, still slowly winding and unwinding along its orbit, the stars spreading further apart with every passing million years, but still, for now, for a few billion years more, recognizable as a coherent structure, as a family, as the ghost of something that once existed. By the time Gaia and surveys like S5 had done their work, the count of known stellar streams in the Milky Way's halo had passed 50. And it is still rising. 50 distinct ribbons of stars, 50 forensic records of objects destroyed, 50 chalk outlines on the floor of the galaxy. Now here is something worth pausing on. Because there is a story that gets told about galaxies like ours, a word that gets used, and it is technically true, but subtly wrong in a way that matters. Cannibal. You will hear the Milky Way described as a cannibal galaxy. The image it conjures is vivid and fast, one galaxy opening its mouth, swallowing another whole, and it's done. Quick, clean, a galaxy devoured. But that is not what happens. What actually happens is closer to something you might call slow unraveling. When a smaller galaxy or a star cluster falls into the Milky Way's gravitational field, it does not get swallowed in an instant. It gets tugged. The tidal forces begin to pull at it on every pass. Stars start to leak from the edges. A few at first, then more, the stream gradually filling in, orbit by orbit, the cluster or dwarf galaxy losing mass slowly. Shedding stars the way a sweater slowly loses threads when it catches on something rough. The Sagittarius Dwarf Spheroidal Galaxy, the one whose stream wraps the whole sky. The most dramatic example of all has been plunging through the Milky Way's disk repeatedly for billions of years. Each time it passes through, it loses more stars to the stream, bleeds more of itself into that great encircling ribbon. But it hasn't been swallowed. It still exists as a recognizable, gravitationally bound object, even if it is greatly diminished. Even if it is being continuously dismembered. The eating is not a gulp, it's a long, slow dissolve. The meal is still arriving, the digestion is ongoing, and will continue for a long time yet. This matters because it changes the picture of what you are looking at when you look at a stellar stream. You are not looking at the aftermath of something finished. You are looking at a process still in motion, frozen for you only because the timescales involved, hundreds of millions of years, billions of years, are so vast that from your position, looking up from Earth on any given night, the ribbon appears perfectly still. The stream is moving, the stars in it are orbiting. The Sagittarius dwarf is still falling. But you will never see it move. No human being, no human civilization, no civilization that might arise and last 1,000,000 years will see these ribbons shift by any angle detectable to the naked eye. What you see is a snapshot of a process so slow it is effectively eternal on any timescale that has ever been meaningful to a living thing. And yet it is real. And yet it is happening. The galaxy is not a static arrangement. It is an ongoing event, a long, slow story still being told, and the streams are its current chapter. That thought can settle gently if you let it. There is something almost peaceful about timescales this long, the knowledge that the drama is real, the collisions genuine, the reshaping of a galaxy a true and ongoing process, and yet the night sky is utterly serene. Nothing rushes. Nothing lurches. The ribbon wraps the whole galaxy, and the galaxy holds it quietly, the way old things hold the marks of everything that shaped them, without announcement, without urgency, without any sign at all of what they have been through. Some of the stars in these streams, some of the inherited stars now orbiting in the Milky Way's halo, donated by the galaxies that fell in, are among the oldest objects in the galaxy. Older than 12 billion years. Stars that formed in the early universe in the compressed and violent first few billion years after the Big Bang. Inside dwarf galaxies that were already old when they encountered the Milky Way, already carrying within them this ancient stellar population that our galaxy would eventually absorb. In a very specific, literal sense, the Milky Way inherited antiques. Stars older than the disk it spins. Stars older than the Sun by many billions of years. Now orbiting in our halo because the galaxies they formed inside were pulled apart and their contents folded into ours. When you look at the faint smudge of the stellar halo, that diffuse, barely visible sphere of old stars surrounding the bright disk, you are looking at a graveyard and a library at once. The disassembled bodies of galaxies that no longer exist, whose stars now orbit inside something larger, still carrying the memory of where they were born. There is a word for this field. We mentioned it at the start, and it is worth saying again now that you have a sense of what it means. The discipline is called galactic archaeology, sometimes also near-field cosmology. Both names point to the same thing, the idea that the history of the universe is not only written in the distant ancient light we observe across billions of light-years of space, but also written locally, here, in the motions and chemistries of the stars surrounding us. That the Milky Way itself is an archive, that if you know how to read it, know how to look at an orbit's shape, a stream's arc, a star's chemical composition, a retrograde motion against the grain, you can reconstruct events that happened billions of years ago, events no one witnessed, events that left no photographs and no recordings, only the slow, patient, unchanging testimony of stars still moving as they were set in motion long before anything on Earth existed to notice. And so, let us name some of those meals. Let us walk through a few of the identified remnants, the ones that have been pulled from the archive and given names. Because one of the quiet marvels of this whole discipline is that these things have names at all. That what began as faint smudges and statistical overdensities in a survey image now has a catalogue. A growing list of objects that no longer exist as objects, but whose outlines are still legible if you know where to look. We have already spent time with Sagittarius, the giant, the ongoing disruption, the stream that wraps the whole sky. But Sagittarius is, in some ways, the obvious one, the loud one, large enough and recent enough in its disruption that it announced itself early. The others required more patience. Around 8 to 11 billion years ago, so early that the Milky Way was still assembling itself, still a young and relatively compact thing, not yet the broad spiral it would become, there was a collision of a different kind. Not a small dwarf brushing past, but something more substantial, a significant merger. A massive dwarf galaxy, now called Gaia-Enceladus, falling in and being absorbed. The name comes from two sources, the Gaia spacecraft, which revealed it, and Enceladus, one of the titans of Greek myth, a figure buried beneath a mountain, which is fitting in its way. This ancient galaxy was not merely passed through, it was swallowed, buried inside the Milky Way, its stars folded into the inner halo, its identity erased as a separate object. Gone, What remained was a signature: stars on particular orbits. When astronomers plotted the velocities of stars in Gaia's data, mapping their motions in 3 dimensions, a certain population stood out. Stars moving on elongated radial paths, back and forth, in and out, plunging toward the center and swinging back out again, over and over. In velocity space, this population forms a blob, a stretched shape. And so it earned a second name, a more affectionate one, the Gaia sausage. Because in the diagrams, that is precisely what it looks like. The Gaia sausage is not a stream in the spatial sense, it is a dynamical population, a set of stars sharing a family resemblance in how they move, even now scattered through the inner halo. But the idea is the same. These stars carry the memory of a galaxy that no longer exists, and that memory, written in velocity space, is how we know the collision happened at all. One of the last major mergers before the Milky Way's growth slowed. One of the formative events that built the halo we now inhabit. There is another, slightly smaller, slightly earlier, discovered in a different way. In 1999, a Dutch-Chilean astronomer named Amina Helmi, working with her colleagues, identified a group of stars near the Sun moving in a distinctive looping pattern. Stars that, by their velocities, clearly did not form here. They shared orbits that said, "We came from somewhere else, we arrived together, we are the remnants of a system that was pulled apart 6 to 9 billion years ago." These are the Helmi Streams, historically important because they were among the first fossil mergers ever reconstructed purely from stellar motions. Long before Gaia, long before the catalogues. A proof of concept, quietly inserted into the literature while most people were thinking about other things, that this kind of archaeology was possible at all. And then there is Sequoia. Not a stream in the visual sense either, but a population distinguishable by its motion. A set of stars on retrograde orbits, orbiting the Milky Way in the opposite direction to the disk's rotation. Backward, and as we discussed, backward motion in this galaxy is a strong indicator of foreign origin. These stars did not form inside the Milky Way's own rotation. They were contributed by a separate dwarf galaxy, accreted at some point in the distant past. Their chemistry and their orbits together telling us they came from a different place than Gaia-Enceladus. Another meal, another name, another entry in the catalogue. There is also a candidate, debated, carefully framed, but genuinely fascinating, sometimes called Kraken, or Heracles, depending on the paper you read. The suggestion, derived from the ages and orbital properties of certain ancient globular clusters that seem to belong to a single accreted system, is that there may have been an even earlier major merger, earlier than Gaia-Enceladus, possibly more transformative in its effect on the young proto-Milky Way. The identification is statistical, not yet definitive. The merger itself left no single dramatic stream to point at and name cleanly. What it left, if the reconstruction is correct, is an imprint on the globular cluster population, ancient clusters orbiting in ways that suggest they were carried in from outside. This one we hold gently. A leading candidate in an ongoing debate, not a settled chapter, but worth naming because the uncertainty itself is honest. The archive is not fully decoded. There are pages we are still working to read. Now, the Orphan. Or rather, the Orphan-Chenab stream, as it is more often called now. This one earned its original name, the Orphan Stream, because for years after its discovery, no one could identify its parent. A trail of stars, clearly a disrupted system, but with no obvious galaxy of origin still intact. An orphaned ribbon. The name stuck, even after the parent was tentatively linked to a region associated with a small dwarf called Gruz 2. And the stream itself has something else interesting about it. A kink. A wobble, a deviation from the smooth arc a freely orbiting stream would follow if the only thing acting on it were the Milky Way's own gravity. The leading explanation for this wobble is the Large Magellanic Cloud, that nearby companion galaxy, massive enough to tug on the whole dark matter halo and bend trajectories that would otherwise run straight. The Orphan Stream's kink is, in this reading, the fingerprint of the Magellanic Cloud's gravitational pull, recorded in the positions of stars in a completely different stream. Gravity leaving a note in the margin of someone else's story. The Magellanic Clouds themselves, the large and the small, those two companion galaxies visible to the naked eye from the southern hemisphere, bright smudges in the night sky, are future meals, still intact, for now. But already being pulled, already leaking. The Magellanic Stream, a vast ribbon of gas trailing behind them across more than 100 degrees of sky, is the early evidence of disruption. Not stars yet, mostly gas, being drawn away by the Milky Way's tidal pull. The clouds are on a trajectory that will eventually end in absorption. But eventually here means something far beyond any human timescale. For now they orbit, and they leak, and they bend the streams of older, already dissolved objects as they pass. Then there are the quieter entries. Palomar 5, Pal 5, a globular cluster caught mid-destruction, trailing tails tens of thousands of light-years long. A textbook case, used to demonstrate the mechanism, the two tails, the leading arm ahead, the trailing arm behind, exactly as the physics predicts. And the Phoenix Stream, from a globular cluster whose stars carry a chemical composition that is almost startlingly pure. Very low in heavy elements, a cluster from the very early universe, it seems, preserving a chemistry that speaks to a time before many generations of stars had lived and died and seeded space with the heavier atoms they forged. The Phoenix Stream is in some ways a message from an earlier epoch of the cosmos, still legible in the abundance ratios of stars now drifting in our halo. And the S5 threads. The Southern Stellar Stream Spectroscopic Survey, S5 for short, named its discoveries after rivers. Jhelum, Indus, Ravi, Elqui, Atlas, thin, cold ribbons, some only a few degrees wide on the sky. Each one the shredded remnant of a globular cluster or small system, each one a faint pencil line drawn across the southern sky by something that no longer exists. The catalogue now runs to more than 50 named and candidate streams. More than 50. And every single one of them, no matter how thin, no matter how faint, no matter how far they drape across the southern or northern sky, carries a secret beyond its own existence. Because these ribbons are not just the evidence of old crimes, they are instruments, and what they measure is something that cannot be seen at all. Let's drift toward that now, slowly, no rush. You've probably heard that most of the Milky Way is invisible, not dark in the way a cloudy night is dark, not empty in the way a room is empty. Invisible in a stranger, more complete sense. The stars you can see, the ones mapped by Gaia, the ones seeded in streams across the halo, all of them together, all the gas, all the dust, all the raw material that will one day become new stars, it accounts for only a fraction of the galaxy's total mass. The rest is something else, something that does not glow, does not emit light, does not absorb light, does not show itself to any telescope we have ever built. We call it dark matter, not because we're being poetic, but because we have no better name for something that refuses to announce itself. And yet, the Milky Way is wrapped in it, surrounded by it, threaded through it. The best estimates suggest the galaxy sits at the center of a vast, roughly spherical halo of dark matter, not the stellar halo of old stars and stream debris we've been wandering through together, but a gravitational halo that extends far further, far beyond any star, any stream, any known object. Its total mass is on the order of 1 trillion solar masses, 1 trillion times the mass of our own sun, spread through a volume we cannot see, in a form we cannot directly detect. That's the thing lying there, patient, in the dark. And for a long time, we didn't know how to weigh it. Not precisely. You can infer something is there from the way the galaxy rotates. Stars at the edges of the disk move faster than they should if only visible matter were present, which tells you something unseen is holding them in. But that gives you a rough estimate, not a map. It doesn't tell you the shape. It doesn't tell you how the mass is distributed as you move further out into the deep halo where there are almost no stars left to track. This is where the streams come in. Think of a stellar stream as a plumb line hung in the galaxy's gravitational field. When a plumb line hangs in a uniform gravitational field, it drops perfectly straight. But if the field is uneven, if the mass around it is arranged in an odd shape, tilted, flattened, pulled to one side, the line curves, and the curve tells you the shape of the field, even if you can't see what's producing it. A stellar stream does exactly this, across scales that beggar imagination. The stream arcs through the halo, curving as it goes, following the groove carved for it by the total gravitational field it moves through. Not just visible matter, not just stars, everything, and if you can measure the arc precisely enough, the exact path the ribbon traces as it sweeps through the halo, you can work backward to the distribution of mass that must have produced it, including the invisible mass, including the dark matter. The Sagittarius stream has been one of the primary instruments for this work. It wraps more than 360 degrees around the galaxy. Remember, a complete loop, a whole dismembered dwarf galaxy, unspooled into a ribbon that circles our own. And when astronomers measured that arc, comparing the observations to thousands of different model halos in their simulations, adjusting the shape and mass until the model matched the real ribbon, what they found was remarkable and strange. The dark matter halo does not appear to be a perfect sphere, not evenly round, like a soap bubble, but something called triaxial, squashed and stretched differently along all 3 axes at once, like a potato rather than a marble. Elongated one way, flattened another, tilted relative to the disk of the galaxy. You would never know this by looking at the visible galaxy. The stars and gas don't tell you, only the Sagittarius stream, curving in 3 dimensions across the whole sky. Tracing the shape of the invisible medium it swims through can suggest something like that. And it's not settled. That's honest and worth saying. The exact shape of the dark matter halo is still actively debated. Different models, different measurements, different assumptions about how the halo may have shifted, as the Milky Way swallowed its meals, produce different answers. The Magellanic Clouds, as we talked about, are massive enough to be tugging on the halo itself, distorting it from its original form. The Milky Way's dark matter halo is not a static, pristine sphere. It's being pulled and sloshed as the clouds spiral in. So measuring the shape is partly a matter of catching a moving target. But the point stands. The stream is the instrument. Without it, we would have only rough estimates. With it, we have a measuring tape laid across 100,000 light-years of invisible material. The outer halo is another reason streams matter so much. As you move further from the galactic center, out past 10,000 light-years, out past 50,000, out toward the edges of the stellar halo, there are almost no stars, almost nothing to use as a gravitational tracer, nothing to watch move in a way that reveals what's pulling it. The empty outer halo has been, for most of astronomical history, almost impossible to weigh. But a stream that extends into those distances, and Sagittarius does, it sweeps far out from the plane, carries information about the enclosed mass at those distances. It extends the scale out into empty space. It lets us measure what we cannot see, in a place where there is almost nothing to measure. So 50-odd named streams are not just a catalogue of ancient meals. They are a distributed network of measuring instruments threaded across the galaxy, and each one is silently reporting something about the dark architecture it moves through. Now, there's a particular stream we should return to because it offers the strangest and most beautiful demonstration of what streams can reveal. GD1. You'll remember it. The thin one, the cold one. The remnant of a globular cluster rather than a full dwarf galaxy, which is why it's so extraordinarily narrow, a wispy thread roughly 100,000 light-years long, but only a handful of light-years across in some places. Because globular clusters are small and dense, with no dark matter of their own to puff them up, their streams are cold and tight and whisper-thin. And that thinness is precisely the property that makes them so sensitive. A cold, thin stream should be smooth, even like a length of thread laid across a table, unruffled, undisturbed. The math of tidal disruption says that stars leak from the cluster at a steady, gentle rate, and they string out along the path ahead and behind in a regular, continuous ribbon. There should be no gaps. There should be no sudden missing patches. And when astronomers examined GD1 carefully with Gaia data, they found something that shouldn't be there. A gap. A place where stars should be and simply are not. A hole in the thread, as if something had reached into the ribbon and plucked a handful of stars aside. And alongside the gap, drifting just off the stream's main track, a little cluster of stars that shouldn't be there either. A spur. A faint knot of material displaced from the main ribbon, sitting off to one side as if something had nudged it. The leading hypothesis, and it is a hypothesis, carefully tested against simulations, not yet a settled fact, is that a dark matter subhalo passed through the stream. Let me try to make that vivid, because what it means is extraordinary. Cold dark matter theory, the standard model of cosmic structure formation, predicts that the Milky Way's dark matter halo is not smooth. It should be lumpy. Full of smaller clumps, smaller halos nested inside the big one, a whole architecture of overdensities in the dark medium. Thousands of them, potentially tens of thousands, orbiting inside the galaxy's dark halo. And these subhalos can contain very few stars, or no stars at all. If they formed too small, too early, or in an environment where ordinary matter couldn't cool and clump inside them, they remain dark. Invisible, we cannot point a telescope at them. We cannot photograph them. We cannot directly detect them with any instrument we have. And yet, if they are there, they move. They orbit inside the dark matter halo, swinging around the galaxy on their own paths, and occasionally, very occasionally, one of them passes through a stellar stream. When it does, if the model is right, it is like a stone dropped through a silk thread. The gravitational pull of the subhalo, arriving and departing over some thousands or millions of years, yanks the nearby stars sideways. It creates a gap in the ribbon where stars were pushed away, and it creates a spur, a displaced cluster of those pushed stars, drifting off the main track like scattered thread ends. That is what GD1 appears to show. A dark mass punching through a ribbon of stars and leaving its shadow in the form of an absence. A footprint without a foot. A dent without a rock. And if that interpretation holds as more data comes in, it would be something genuinely profound. Because it would mean that these thin, cold streams are not just measuring the smooth, average gravitational field of the dark halo. They are sensitive enough, quiet enough, undisturbed enough to register the passage of individual dark clumps. Invisible objects below the threshold of any direct detection, announcing themselves only by the damage they leave in a ribbon of stars. Streams as seismographs. The galaxy's outer skeleton vibrating when something massive and dark passes through. The standard cosmological model predicts thousands of these dark ceballos. We've never seen them directly. We can't. But if thin streams are the instruments that can read their passages, if the gap in GD1 is one footprint, and if Rubin and future surveys reveal more streams with gaps and spurs, then we are on the edge of verifying a fundamental prediction about what dark matter actually is and how it behaves. We are, or we may be, on the verge of reading the galaxy's darkness by the way it bruises the light. That's not settled science yet. It's a live question, actively being worked, but it's one of the most exciting live questions in modern astrophysics, and the fact that it's even askable that a ribbon of stars from a dead globular cluster could serve as a detector for invisible dark matter clumps is itself extraordinary. There's something else the streams have shown us, something closer to home. The Sagittarius Dwarf didn't fall into the Milky Way just once. It has been plunging through the disk repeatedly, orbiting inside our galaxy, each orbit taking it swinging around and back. And each time it passes through the disk, through the flat, dense, star-rich plane where we live, the encounter does something to the disk itself. The disk is not rigid. It's made of gas and stars moving in a gravitational field, and when something heavy passes through it on a roughly perpendicular path, the impact is real. The disk flexes. Ripples move outward. The plane shifts up and down in waves, something like the surface of a lake after a stone is dropped in. And those waves don't die out immediately. The disk is still resonating. In 2018, astronomers looking at Gaia data found something strange and beautiful in the motions of stars near the Sun. When they plotted the stars by two quantities, height above or below the midplane of the galaxy, and the velocity at which they were moving up or down, they expected a simple, settled distribution. A smooth pattern indicating stars in quiet orbits. Instead, they found a spiral. A snail shell shape, a pattern wound through the data like the coil of a galaxy in miniature, right here in the local neighborhood. It came to be called the Gaia phase spiral, and what it represents is exactly that ringing. The disk, disturbed by a gravitational impulse, doesn't snap back to equilibrium all at once. Different stars, at different positions and velocities, respond at different rates. Over time, the disturbed distribution winds itself into a spiral pattern, precisely as you'd expect from the mathematics of a system responding to a disturbance and slowly mixing. The best models suggest the disturbance happened somewhere between a few 100 million and roughly 1 billion years ago. The timing matches a Sagittarius passage. Not the original infall Sagittarius has been plunging through for billions of years, but a more recent encounter, one close enough and forceful enough to imprint a pattern on the stellar velocities near the Sun that Gaia, billions of years later, has now read out. The disk is still ringing. We can hear it in the data. And that is, in some ways, the most personal moment in this whole story. Because the sun is here, embedded in the disk, moving through a neighborhood of stars that are still, slowly, responding to the impact of a galaxy that fell through billions of years before any of us were born. The phase spiral is written in the motions of stars all around us. Sagittarius passed through, and the galaxy is still rippling from it, and we are inside the ripple. That's not a metaphor. The motions are real, the pattern is measured, the data is in the archives. We live inside the aftermath. Now let me tell you one more thing, and then we'll let this settle. The stellar halo, the vast, diffuse sphere of old stars surrounding the disk, the region where the streams live, is thought to be built substantially from these accreted, shredded objects. Not entirely. The galaxy formed its own early stars too. But a large fraction of the halo's stars are immigrants, the disassembled bodies of galaxies that fell in and were torn apart. Objects that no longer exist anywhere as coherent things. They've been absorbed, incorporated, redistributed through the halo in ribbons and shells and the blurred-out remains of ancient encounters. And some of those stars are extraordinarily old. When a dwarf galaxy falls into the Milky Way, it brings its own stellar population with it. Stars it formed during its own early history, back when the universe was young. Some of the stars in these swallowed dwarfs, stars now drifting in our halo, perhaps mixed into some of the streams, perhaps in the shell of Gaia-Enceladus debris, are more than 12 billion years old. Older than the Milky Way's own disk. Older than the structure you and I live inside. The disk of the galaxy is thought to have formed perhaps 8 to 10 billion years ago, after earlier mergers had already occurred, after the halo was already being seeded by the debris of infalling objects. So there are stars in our halo that predate the structure of our galaxy. Antiques, heirlooms from galaxies that no longer have names, from objects that ceased to exist billions of years before the Earth formed, before the sun ignited, before any of this, their old light still crossing the sky. We inherited them. The Milky Way swallowed a galaxy that had already been making stars for 1 billion years, and those stars became ours, added to the halo, mixed into the fossil record. In some sense, we are, in part, a composite of objects long gone. And a few of the oldest stars visible from Earth, the ancient iron-poor suns that formed in the very early universe, may have been born in a different galaxy entirely. That thought is worth carrying a moment. A star older than our galaxy, now part of our galaxy. An inherited ancestor. The halo as inheritance. The halo as the accumulated material of everything that fell and was taken apart, billions of years of encounters encoded not in some file or document, but in the motions of stars. In the chemical ratios baked into their interiors, in the subtle arcs of their orbits, in the faint ribbons they form as they drift through the darkness around us. Galactic archaeology, near-field cosmology. The terms for a discipline that didn't quite exist before the data existed to make it possible. Before Gaia turned the sky into a movie, before chemical surveys gave each star a fingerprint, before N-body simulations could replay collisions on a computer screen. Now it exists. Now the halo is readable. Not fully, not yet completely, but more than ever before, and more with every year of new data. And there is more coming. The Vera C. Rubin Observatory in Chile, with its enormous mirror and its plan to photograph the entire southern sky over and over again, is expected to find streams we have never seen. Faint ones, old ones, structures so diffuse and stretched and ancient that no previous survey had the depth or the sky coverage to pull them out from the background. The count of named streams passed 50 not long ago. When Rubin reaches full operation and begins its survey, the legacy survey of space and time, astronomers expect that number to grow, perhaps by a lot, perhaps to dozens more, perhaps to structures we can't currently imagine, because we've never had the instrument to see them. The catalogue of the Milky Way's forgotten meals is not finished. It may not even be half finished. Everything we've discussed tonight, the Sagittarius Stream, Gaia-Enceladus, the Helmi Streams, Sequoia, the Orphan-Chenab Stream, Pal-5, Phoenix, GD1, the 50-odd river-named threads, all of that may be the visible tip of a much larger record. The halo holds its history more patiently than we've been able to read. There will be more pages. The book is still being opened. And somewhere in that future catalogue, there may be streams with gaps that confirm what GD1 has hinted. Footprints of dark subhalos registered in missing stars. The invisible matter of the universe, finally announcing itself not by glowing, not by interacting, but by leaving the faintest possible dent in a faint possible ribbon of stars. If that day comes, and it may, it will have been the streams that made it possible. The slow, patient, 3-billion-year archives of tidal disruption, waiting for us to build instruments good enough to read them. We're building them now. Let me try to bring all of this together, here, in the quiet. We started tonight with a discovery made in 1994. Rodrigo Ibata, Gerard Gilmore, and Michael Irwin studying stars near the Milky Way's center, realizing that something was wrong, that a population of stars didn't belong there, couldn't have formed there, must have come from somewhere else. And when they traced it, they found a whole dwarf galaxy in the process of being torn apart. The Sagittarius Dwarf Spheroidal Galaxy, falling through the Milky Way, bleeding stars from its 2 tidal gates, the leading arm falling ahead, the trailing arm falling behind. A galaxy-scale catastrophe, playing out so slowly that no human, no civilization, no being with a biological lifespan could ever watch more than a vanishingly small fraction of it occur. But spread across the sky as a ribbon, a complete loop, a wound around the whole Milky Way, there for us to read. And we found that it was not alone. The halo is threaded with these things, more than 50 named ribbons of stars, each one the shredded remnant of something that once had its own gravity, its own history, perhaps its own planets, its own faint story that ended when the Milky Way's tidal arms reached in and pulled it apart. Gaia-Enceladus swallowed 8 to 11 billion years ago, its debris forming the elongated, radial population that built the inner halo. The Helmi Streams, reconstructed by Amina Helmi from stars near the Sun, sharing a distinctive looping motion, a dwarf galaxy consumed 6 to 9 billion years ago. Sequoia, orbiting backward, its retrograde path a signature of foreign origin. The Orphan-Chenab stream, bent and kinked by the gravitational pull of the passing Magellanic Clouds. The Phoenix Stream, carrying the chemistry of the very early universe. The S5 threads, Jhelum, Indus, Ravi, Elqui, thin cold rivers named for rivers on Earth, flowing invisibly through the southern sky. And woven through all of them, the question that gives them their deepest meaning. The dark matter halo, 1 trillion solar masses of invisible material surrounding the galaxy, unmeasurable by ordinary means, unreachable by ordinary instruments, but reachable through the streams. The Sagittarius arc argues for a triaxial halo, not a sphere. The streams in the outer halo measure the enclosed mass in a place where there would otherwise be nothing to measure with. GD1's gap and spur, a missing patch of stars, a displaced cluster floating beside an absence. Whispers of something dark that passed through, something that left a shadow made of missing light. Streams as measuring tape, streams as seismograph, streams as crime scene evidence, all three at once. And one more thing. The disk near the Sun still bears the phase spiral, the snail shell wound into local stellar velocities, a pattern that is still slowly unwinding from an encounter that happened hundreds of millions of years ago. You are sitting inside a ripple that Sagittarius left in the floor of the galaxy. Every star you can see from a dark sky site is moving, right now, in an orbit still gently disturbed by that ancient passage. The galaxy remembers, and I mean that as a metaphor, as a piece of narration color. Not as a claim, the galaxy preserves, in its physics, the shape of what happened to it. And we are part of that preserved record. Because the Sun is here, inside the disk, inside the halo's inner edge. When Sagittarius streams past the galactic poles, when its shredded stars arc through the regions directly above and below the plane of our galaxy, those stars are overhead. Not in the bright band of the Milky Way we see stretching across a summer night, but in the quieter, darker patches of sky near the poles of the galactic axis. In a very real sense, if you have ever lain on your back on a dark night and looked up at a sky full of stars, some faint speck of light in your field of view might have been born inside the Sagittarius Dwarf Spheroidal Galaxy. A star from a galaxy that no longer exists, now arcing gently through ours, on its way to being fully absorbed. You were looking at a refugee, without knowing. That's what the sky is. Not just a static display of distances and magnitudes and ancient light. A living archive, a crime scene still being processed, evidence still being catalogued, measurements still being made. Gaia, hovering at the L2 point 1.5 million kilometers from Earth, is still measuring. The data releases still come. The streams are still being found, refined, disentangled from one another when they overlap. The simulations are still being tuned. The phase spiral is still unwinding. The Rubin Observatory is still being readied. The work is ongoing. The archive is still being read. And when you think about what that means, not just the streams themselves, but the act of reading them, there's something quietly astonishing in it. Human beings on a small planet orbiting an ordinary star in a spiral arm of one galaxy among hundreds of billions of galaxies have worked out how to rewind the history of that galaxy's past mergers. How to take the current positions and velocities of stars, add up the forces, run the simulation backward, and watch a galaxy that hasn't existed for billions of years get torn apart, frame by frame, in a computer model. The galaxy absorbed the evidence. The stars preserved it. We learned to read it. Galactic archaeology. That's what the discipline is called. And it's real. And it works. I find that remarkable. I hope, drifting wherever you are tonight, you find it remarkable too. There's something even more personal in this, if you want it. The halo is made, in large part, of stars from elsewhere. Immigrants, debris, inherited antiques, older than the disk we live in. And the sun, your star, the warm yellow thing that makes everything on Earth possible, formed inside the disk, from material that had been partly seeded by earlier stellar generations, some of which were themselves the heirs of swallowed galaxies. We are not purely the offspring of one galaxy with a single clean lineage. We are a composite. A mix. A thing built, partly from the remains of things that gave their material to us without consent and without knowing. In some small way, the Milky Way's history is our history too. The universe has been doing this for a very long time, forming structures, pulling them together, tearing them apart, incorporating their material into new things which do the same to other things. The cosmic web, the filaments of dark matter, the halos, the galaxies, the streams. It's disruption all the way down, and what you get from it, eventually, is the kind of ordered complexity that can look up at the sky and try to figure out where it came from. And what we get, if we look carefully enough, is something like an answer. The halo is a fossil record. The streams are the legible parts, and Gaia gave us eyes fine enough to read them. If this slow drift through the dark has helped your night settle, if the galaxy felt a little less distant and a little more familiar as we wandered through its past meals and its invisible architecture, I'm glad. A like and a subscribe means more than you might think. Small channels like this one rely on that quiet, low-pressure support to keep going. And if you'd like to tell me where in the world you're listening from and what the night looks like from your window, I'd love to know. That's always my favourite part. The streams will be there tomorrow. Gaia will still be measuring. The Rubin Observatory will eventually open its eyes and find the meals we haven't catalogued yet. The galaxy is patient. It has been collecting its archive for more than 10 billion years. A night's rest won't change anything it has recorded. So rest. Let the dark matter halo sit around you, invisible and patient and enormous. Let the phase spiral unwind slowly in the data, as it has been for hundreds of millions of years. Let the stars of the Sagittarius stream drift overhead, faint and ancient and far, doing what they've been doing since long before the Earth existed. You're inside the crime scene. But it's a gentle one, and it's very, very old. And you have time. Close the books, dim the lamp. Class is over. Sleepy scholar.